Hello and welcome to Insight Ophthalmology. This is Dr. Amrit and today we are studying a very important topic for the beginners and especially in refraction, and the topic is retinoscopy. We shall be discussing how can we actually master retinoscopy and actually become a retinoscopy detective. So without any delay, let's get started with the basics of retinoscopy. First, you should know what are the methods of refraction. Under various methods of refraction, we have the objective ones and the subjective one. The subjective methods of refraction are those in which the refraction actually depends upon the responses from the subject, that is our patient. And the objective form of refraction is a refraction which is free from the patient bias, that is free from the patient answers. And basically it is of two types. Either you can have a computerized method, that is in modern times called the AR machine or the autorefractometer, or since times immemorial what we are doing is the retinoscopy. So what is retinoscopy? Retinoscopy is nothing but it is a type of objective method of refraction. Retinoscopy is an age-old technique and it is known by a lot of names. It is also called the skioscopy or the shadow test. It is called the umbroscopy, the scotoscopy and the pupilloscopy. So all these are the synonyms for retinoscopy. Now before I take you into the depth of the concept of retinoscopy, it is very important to know certain sub-concepts, certain basics. So starting with the far point of the eye. So what is meant by the far point of eye? The farthest point from the eye which can be seen clearly with accommodation at rest is called the far point of the eye. So when you take an emmetrope, the far point is basically present at infinity. So what we mean to say is a normal eye which does not have any refractive error will be able to see almost up to infinity. Next, we talk about the myopes. We know that myopia is also known as the nearsightedness. So in myopia, what happens is that the far point is actually located in between the infinity and the eye. So what I mean to say is that the far point is not at infinity, but at a distance which is much less than the infinity in case of myope. Coming to hypermetropia, hypermetropia is called as the long-sightedness, and in hypermetropia the far point is present beyond infinity. Okay, so what happens exactly in hypermetropia is that the image is going to be formed behind the retina in case of hypermetropia. So that image acts as a virtual object, and then the rays of light from that image will actually seem to be coming from beyond infinity, and that is the reason that the far point of hypermetropia is said to be beyond infinity. Now these three things are very important for you to know and to understand retinoscopy. Let us now try to understand the concept of conjugate foci. Conjugate foci are two focuses which are actually present, one in front of the lens and one is present behind the lens, and they are placed equidistant from the lens surface. Now if you place an object at the first foci, the image will be formed at the second foci. Similarly, if the object was to be placed on the second foci, the image will be formed on the first foci. So both of them can actually act alternatively and in place of each other. So the rays which are originating from one will definitely converge on the other, and again vice versa. Such foci are called conjugate foci. Now in a normal eye, the far point is said to be conjugate with the fovea. So what I mean to say is the images which are coming, the rays which are coming from the far point, they will focus on the fovea. Similarly, the rays which are originating from the fovea, they will go up to the far point to converge at the far point, which is considered to be infinity for a normal eye. So as we know, in a normal eye which does not have any refractive error, the far point is infinity, and the conjugate point for this far point will be actually the infinity. So the rays which are coming from the fovea, if the fovea was supposed to act as a object, the image will be formed at the infinity, and as we know that the rays which are coming from infinity, their divergence is mostly parallel rays, and therefore the rays will look parallel in their vergence. So let me here introduce you to a concept of vergence. Vergence is nothing but it is the orientation of the rays. So if you consider an eyeball like this and consider an object which is present very close to the eyeball, the rays which are coming from that object will be basically diverging in their nature. However, if the object is present very far away from the eyeball, the rays which are coming from that object will be now not very diverging, instead they will be less diverging. Okay, similarly, as you keep on moving away from the eyeball towards infinity, the orientation of the rays will become more and more parallel in orientation. Okay, so this is the concept. Now, let us talk about the myopic eye. In myopic eye, we know that the image is not formed onto the fovea. Instead, the image will be actually formed in front of the fovea, that is over here. Okay, the image is formed in front of the fovea. So as I told you, the conjugate point for the fovea or for the focusing point should be actually the far point. Now the far point in a myopic eye is present in less than infinity. That means a patient who is suffering from myopia actually has short-sightedness. He cannot focus the images placed at infinity, but at he will be actually able to see clearly up to a certain distance, and that distance is called the far point for that myopic patient. So the far point in myopic patient is less than infinity, and therefore that is the conjugate point for that patient. That means if the images were to come, if the rays were to come from this point over here, considering this to be the focus of this myopic eye, the rays will finally come at this location, say A. Okay, so A is the conjugate foci for the myopic eye, and which is less than infinity. Now coming to the hypermetropia. In hypermetropia, we know that the rays will actually come to a focus at a point which is actually placed behind the eyeball. Okay, so it is placed basically behind the eyeball. Okay, the focus is behind the eyeball. So the conjugate foci, where will it be? The conjugate foci will be more than infinity. It is present even beyond the infinity, where we actually cannot go and measure it. So the orientation of rays will also be more of parallel or more diverging orientation. So remember, in emmetropic eye, the conjugate focus is at infinity. In a myopic eye, the conjugate focus is less than infinity, and in hypermetropic eye, it is more than infinity. And the orientation of rays in the emmetropic eye is parallel orientation. In a myopic eye, it is the converging orientation. And in case of the hypermetropic eye, since they are going even beyond infinity, they are basically the diverging rays, which will actually never meet. So they have a diverging orientation or divergence. So how does the retinoscope basically work? So in a retinoscope, we direct a light into the patient eye. Okay, and by directing the light into the patient eye, we are basically illuminating the retina. Now these rays of light from the patient's retina will emerge from the patient's pupil and form an image. Where will they form an image? They will form the image at the far point of the patient eye. Why? Because the retina will have a conjugate point, as I explained, and that will be the far point of the patient eye, where the image will now form. Okay, now the location of this image will depend upon the refractive status of the eye, as I already explained to you, whether it will be formed at infinity, less than infinity, or more than infinity, and what will be the nature of the rays which are coming from the fovea of the patient or the retina of the patient. Now what we do is we are going to study the rays which are coming out from the eyeball of the patient, okay, by moving our spot or slit, whatever we are using in the retinoscope, and we are going to study those rays which are coming out. And this studying of rays is called studying the behavior of the luminous reflex seen by the observer in the patient's pupillary area. So this is a very basic working of the retinoscopy. Now I'll be telling you in detail what does it mean actually. So there are three phases in the retinoscope. The first one is the illumination phase. In the illumination phase of retinoscopy, we are basically directing the light into the patient's eye so that we can illuminate the patient's retina. The second is the reflex state. Now, the image of an image of the illuminates retina is formed at the far point of the eye. So what happens is we are actually illuminating a part of the patient's retina. Now the retina itself is also going to throw some rays outside the patient's eye, and this image of the retina of the patient will be formed at the conjugate focus, which is the far point of the eye. So in case of a patient who is emmetrope, where will it be formed? It will be actually formed at the infinity. In case of myope, since we know that it will be formed at less than infinity, so the rays will be converging, they will meet at a point and then they are going to diverge again. And in case of hypermetropia, they will always be diverging, so they are said to be meeting at a imaginary point which is beyond infinity, so more than infinity. So this is the reflex state in which the light which we have thrown into the eye will now form an image at the far point of the patient. The third stage is the projection state. In the projection state, the image which is formed at the far point will now be studied by the observer. And how do we study it? We will actually be moving the illumination across the pupil or across the eye of the patient, and then we are going to study the behavior of the reflex in the patient's pupil. Based on that behavior, we will tell what kind of refractive error the patient has. So this is the concept of retinoscopy, which is working on the principle of FOCAULTS principle. So what is this FOCAULTS principle? The principle says that whenever the light is directed into the eye through the pupil, the direction in which the light will move will depend upon the far point of the eye. So let me tell you what does it mean. So as I told you about the nature of the emerging rays which are coming from the retina. Okay, so in the reflex state, what did I tell you? That this part of retina is going to now act as an object and form an image at the far point. Now in case of an emmetrope, the image will be formed at infinity and the nature of the rays will be parallel in nature. Now in case of a patient who is myope, what will happen? The focal point is much less than infinity and therefore the rays will converge at this focus point, and therefore the nature or the vergence of the rays will be converging. In case of hypermetrope, the rays are coming from a virtual point located behind the retina, and therefore the nature of these rays is actually the diverging rays. This is a very important concept that you should remember. So basically, we are acting as detectives in retinoscopy. So we are detectives, we are carrying our retinoscope. With that retinoscope, we are trying to put a slit across. In streak retinoscopy, of course, we are trying to put a light into the patient eye, and then we are moving it across the eye. The eye, in response to our light, is behaving and giving a reflex to us at the far point of the eye, and then we are studying the nature of that reflex. We are studying the movement of the reflex, the speed with which the reflex is moving, and with what brightness that reflex is shining. By studying all these three parameters, that is the direction of the movement, the speed of the reflex, and the brightness of the reflex, we will tell whether the person is normal, whether the person has myopia, hyperopia, or astigmatism. So this is basically your very basic idea of retinoscopy. Now, what are the types of retinoscope? The retinoscopes are basically two types, the mirror retinoscope and the streak retinoscope. This is all based upon the source of light. In mirror retinoscopy, the source of light is basically external. So there will be a bulb usually behind the patient, and from this bulb, the light is going to go onto this mirror and get reflected inside the patient eye, and through a peephole which is present in the mirror, the examiner is going to study the reflex which is seen in the patient's pupillary area. So this is called the Priestley-Smith mirror retinoscope. However, in case of a streak retinoscope, the source of light is actually present within the handle of the retinoscope, and usually it's a bulb with a filament. So it's an internal source of light in streak retinoscopy, and in mirror retinoscopy we have an external source of light. So in the mirror retinoscopy, as I told you, basically we have a plane mirror at one side of the retinoscope, and we have the concave mirror at the other, and these mirrors are going to project a circle of light into the patient's eye through the pupil. So we are actually throwing a circular light into the patient's eye. Now, the idea of plane mirror and concave mirror is that if you would remember from your physics that concave mirrors are basically the converging type of mirrors. So when the light is going to pass through a concave mirror, they are going to cause convergence of a light. Okay, so basically because of this convergence, we are going to get a very focused beam. In case of concave mirror, a smaller but a very focused beam. In case of plane mirror, the plane mirror usually does not cause convergence. It might actually give you the it might just reflect the light rays as they're coming. So if diverging rays of light are coming, you're going to get certain diverging rays of emerging rays also, and they are going to enter the pupil. So in plane mirror, we have more diffuse light, that is diffuse light which is going to enter the patient's eye, and in concave mirror, we have a focused light that is going to enter the patient's eye. So for all purposes, we usually use the plane mirror setting. However, in cases where there is a dense cataract in which the plane mirror might not be able to provide such nice illumination, in those cases, we will go with the concave mirror of the retinoscope. Similarly, we have the streak retinoscopy, in which the streak retinoscope, as shown over here, they actually can convert the source of light and give a streak like this. Okay, so this is a streak of light that we are going to shine across the patient's pupil, and then we can even move this streaks of light in the horizontal direction, in the vertical direction, and in any of the meridians to and fro, screening all the meridians of the eye, and this is called the streak retinoscopy. Now let us break up the retinoscope and see what are the parts of the retinoscope. The main part of the retinoscope is actually the projection system, and the other one is the viewing system. So projection system is basically going to tell you how the beam is projected into the patient's eye, and then we have a viewing system through which the doctor is actually going to see the reflex in the patient's eye. So the projection system consists of a bulb. As you can see here, there is a bulb, and this bulb, just above this bulb, there is a condensing lens. So the image, there is a condensing lens. The rays of light from the bulbs are going to pass through the condensing lens, and then from the condensing lens they are going to reach the mirror. This mirror usually have a hole, and then the rays of light are going to be projected into the patient's eye. Now there is a hole or a peephole which is present here, and the examiner usually sits here looking through the peephole into the patient's pupil. So this is called the projection system. Now, as we talked about the concave mirror setting and plane mirror setting in case of the mirror retinoscopy, similarly we have the plane and the concave mirror settings in case of streak retinoscopy also. But in this case, rather than using the plane and concave mirror themselves, we are going to alter the position of the bulb and the condensing lenses, based on which we have two types of retinoscopes. So let us have a look at the various parts of the retinoscope. So in the Keeler's retinoscope, as you can see here, you have a forehead rest which will touch the forehead of the examiner. Then we have a viewing hole through which the examiner will actually see the pupil. Then we have the adjustable version slide through which you can actually change the plane mirror setting or the concave mirror setting here. Then we have a streak rotator. The streak rotator, which is shown over here, you can rotate this and you can get various directions of the streak. You can get a vertical streak, a horizontal streak, an oblique streak, so on and so forth. And then we have a rheostat or a light source over here. By rotating this, you can actually turn on the retinoscope. Similarly, we have over here the Heinz retinoscope, you can see, and all these are actually the dust-free manufacturing, which is so that the dust can actually not enter these optics. Now the well-shallow one has a fixation card magnet on front where you can actually stick on your fixation cards for doing the near retinoscopy. And again in well-shallow we have a sleeve here. The sleeve can be moved up and down. The sleeve in the Hines is present over here, which can be moved up and down like this. So what is meant by this concave mirror setting and the plane mirror setting, and what is the sleeve up and sleeve down setting of the retinoscope? So what is meant by sleeve? I already told you in the Hines or the Hines, this is the sleeve which is present like this here. You can actually move it up and down and shift between the various kinds of settings, that is a concave and the plane mirror setting. Similarly in well-shallow, this is the sleeve which can be moved up and down. Now, as I told you, in plane mirror, the rays are basically parallel or diverging, and in concave mirror setting, the rays are usually more of converging rays and more focused rays. Now, as I told you that in the streak retinoscope, we do not have the plane mirror and concave mirrors per se. Instead, we have the movable bulb or the lens. Now, in the first type of retinoscope, what happens is we can actually have a retinoscope in which this lens, the condensing lens, will be fixed in position, but the bulb can actually move up and down. So when you actually move the sleeve up, you are moving the bulb up, and when you are doing the sleeve down, the bulb is brought down. So what happens when the bulb goes up? When the bulb goes up, the bulb and the condensing lens are more closer to each other, and the rays and their vergence will become more of a diverging nature of the rays. So as the rays become more diverging, once they go to the mirror, they will have more divergence and they'll be more parallel or more divergence, and this is called the plane effect. So this will act as a plane mirror. Similarly, if you move, however, the bulb down, what happens? The distance between the lens and the bulb will increase, and now as I told you that as the object moves far, the rays which are going towards this will now become more of converging rays, and therefore as the rays will become more converging and less diverging, the rays which are coming after reflecting from the mirror also will be more converging, and this is called the concave effect. So just remember that as the distance between the bulb and the condensing lens decreases, the rays will become more diverging or parallel, and as the distance between them increases, the rays will become more converging. Okay, and converging means concave mirror setting, and diverging means the plane mirror setting. So in the lens fixed type of retinoscope, in which our lens is fixed and we are moving sleeve up and sleeve down, we are changing the position of the bulb. Okay, so as the bulb goes up, that is the sleeve up, we have the plane mirror setting. So this is seen in the Copeland's type of retinoscope. So in Copeland's, what happens is that once you put the sleeve up, it means the plane mirror setting. So basically, if you are using this type of retinoscope, you have to put your sleeve up for majority of your retinoscopies. However, there's another design also in which this bulb will now be fixed, and instead we will move the lens up and down. So if you move the lens up, the distance between the bulb and the lens will increase, and as I told you that as the distance between the lens and the bulb increases, the rays which are coming will become more converging, and we will have a concave effect. But what effect do we want in retinoscopy is the plane effect, and for that it is achieved when the sleeve is moved down. So as the sleeve moves down, this lens is also coming down, and the distance between the bulb and the lens is now decreasing, and as the distance decreasing, the rays are more diverging, and therefore we get a plane effect. So if you are using a well-shallow Hines, Keeler's or Neat's type of retinoscope, it is advisable to put your sleeve down. Okay, so this is very important concept of sleeve up and sleeve down before you start doing the retinoscopy. Now, let us try to understand the reflex basically. Now, as I told you that in a patient who is actually having hypermetropia, what happens in hypermetropia is that the image is formed behind the eyeball, and the conjugate point for this will be more than infinity. Okay, now if we were able to actually sit at this point, at the far point which is beyond infinity, all the rays will converge inside the doctor's eye and we will see a fully illuminated reflex. Okay. However, that is not possible. For most practical purposes, we are going to end up sitting somewhere in between here. Okay. We are going to land up sitting somewhere here. So if we sit somewhere here, what will happen? We are going to actually see the light rays which are coming, and what will be the orientation? They will seem to be converging towards a point, right? So if we sit over here towards the down part, we are going to see the down part of the retina, the lower part of the retina. If we sit somewhere near the upper rays of the retina, we are going to see the upper part of the retina. Okay. Similarly, so what happens with the movement is that in such locations, in such conditions, when the rays are actually they have not yet converged but are converging, and we are standing in path of those rays. If you imagine yourself standing in their path, testing them, then what happens is that we are going to see with movement. That means if you move your retinoscope towards right, you are going to see the right part of the reflex. The reflex will also move towards right. If you move your retinoscope towards left, the reflex will also move towards left side. Since the reflex is moving along with your movement of the retinoscope, and this is happening because the rays have not yet met each other, they have not yet crossed each other, you are going to see a with movement. So this is what I meant. So you are acting as a detective, but here you are actually standing in between the far point and the eye, where the rays have not yet converged. So this is how the with movement looks like. As you move the retinoscope, the reflex is also going to move along with your streak light. So if you move towards right, the retinoscope reflex will also move towards right, and if you move towards the left side, the retinoscope reflex will also move towards the left side, and this is known as the with movement. Now, what will happen in against movement, and why do we see against movement? Okay. Now, in case of myope, let me tell you, you basically see against movement, and why is it so? In myopes, I told you that the image is formed in front of the retina. So as it is not in the fovea, it is in front of the fovea. The far point in myope is also present actually in less than infinity, right? So you can actually sit at the far point of the myope. So what happens if you sit at the far point of the myope? If you sit somewhere here at the far point of myope, all the light rays which are coming, they will actually fall in your eye, and you will have a fully blown, you will not have actually any streak or any reflex. You will actually have a full reflex, fully illuminated reflex, which is called the neutralization point. However, now if you bring your detective again and sit somewhere here where the detective is sitting, what is the detective going to see? The detective is actually now seeing the rays, these rays. If you notice the rays over here, just a second. If you see the rays over here, the lower part of the reflex, if the detective sees, is actually coming from the upper part of the retina. The upper part of the reflex is actually coming from the lower part of the retina. And why is this so? Because the rays of light have already converged before it is going to the detective or to the doctor. Now, because the rays of light have already crossed, the reflex that you see in case of myopes is also a crossed reflex, which is called against movement reflex. That means if you move towards the right, the reflex is going to move towards the opposite side, towards the left, and that is called against movement, right? Now, if your detective was sitting somewhere here, say, okay, what is he going to observe? Then he is going to see with the with movement. Why is he going to see with movement? Because the rays of light have not yet converged with each other, and the detective or the doctor is going to see with movement. If he sits at the neutralization point, he will have the neutralization. If he sits at the far point, he will have a neutralization reflex. If he sits beyond the far point, then he will have against the movement. If he's sitting much before the far point, then he will have with reflex. So in this picture, you can see what is exactly the against movement. You can see how the reflex is moving opposite to the direction of your streak. Now, Now, what about neutralization? What happens in neutralization? Neutralization happens when the image is actually formed on the fovea. So, as I told you, the conjugate point for fovea is infinity, and the rays of light will also be parallel. So, all of these are going to actually enter the eyes of the detector and the detective, and you are going to see a fully illuminated pupil. So this is how the neutralization point is going to look. You're not seeing any you are actually not seeing any streak. You are actually seeing a pupil which is nicely illuminated and equally illuminated in all its quadrants. So this is called neutralization. Now, by changing the direction of the sleeve, as I told you, you can actually change the orientation of the beam. So this is very important, that this over here I have labeled the streak rotator. So by rotating the streak, you can actually sweep various meridian. Now, a very important confusing point which most of the students have is when you are actually putting a vertical beam like this, you are actually testing the horizontal meridian. So this is a very important point. Don't get confused. Okay. So whenever we have a vertical streak and when we are moving the streak left and right, we are actually testing the horizontal meridian. However, when the streak is horizontal, we are actually testing the vertical meridian by sweeping the streak up and down. So I hope that is clear. So the representation of on your power cross that you actually label after doing the retinoscopy will also come like that. So when you are streaking, when you are actually having a vertical streak, which meridian are you testing? You are testing the horizontal meridian. So your power also you will write along the horizontal meridian. So say you are testing with a vertical streak like this, and say at +3 diopters, you get a neutralization point, like the entire thing gets illuminated. So the horizontal meridian over here, you are going to write +3 diopters. However, if the streak is horizontal and you are sweeping up and down, you are actually testing the vertical meridian, and whatever power you get for after neutralization, you are going to write across this horizontal meridian. Okay, next. Now, there is some important dictum that you have to remember, and the dictum is whenever you get an against movement, you have to add minus lenses to reach the neutralization. However, when you get with movement, you have to do vice versa. That means you have to add plus lenses. So let me tell you why do we do that. Now, when do you get against movement? So we know in myopes what happens is when the far point is already reached, the rays have converged at a point and the examiner is sitting beyond the far point. He's actually looking at the rays which have already converged, and we know that in myopia basically the rays are focused in front of the retina, and therefore the far point is also present less than infinity. Now over here, if you add a minus lens, which is a diverging lens or a concave lens, we know that the concave lens will shift the image onto the retina. So as the image is shifted onto the retina, this far point is also shifted to infinity. So therefore, whenever you get against movement, it's an indicator that the patient has myopia, and then you can remember this mnemonic of AM, against movement, and then you have to add the minus lenses. So AM, add minus lenses to reach the neutralization. On the contrary, when you get with movement, we know that with movement occurs when the images are focusing behind the examiner. That means when the far point is located beyond your the place where you are actually sitting, like in hypermetropia, then you have to add plus lenses. That means you will give more converging lens so that the image can be formed somewhere where you are sitting, okay, by giving more convergence ability to this lens. Okay, so therefore with movement you have to do plus lenses. Now what is meant by this working distance? Now to exactly tell you, the far point is present at infinity in case of emmetropes. In myopes, it is present at less than infinity, and in hypermetropes, it is present beyond infinity. Now, you might not be actually able to sit at infinity. So, in order to prevent that difficulty, you might actually sit at a particular distance from the patient eye. So that distance between the retinoscope and the patient eye is called the working distance. Now, if you actually sit at infinity, what happens? All the light rays are going to become very divergent, and the intensity of reflex will become very dull and low. So it is very difficult to notice that such a reflex. Okay, so in such cases, you will sit somewhat closer to the patient, and that distance will become your working distance. So usually the arm's length is taken to be the working distance, which is about 66 centimeters. For people who are short and have short arms, the working distance will usually be about 50 centimeters. Okay, yeah. Now this is how this I've already explained to you. Now let us try to understand what is meant by working lens. Okay, so as we are not sitting at the distance at the infinity, if we were actually sitting at the infinity, we would have actually got the exact retinoscopic values. Now since we are not sitting at infinity, we have to do certain calculations and subtract those values. So what we are calculating is the working lens. Working lens is nothing but 1 divided by working distance in meter will give you a dioptric value, which is called the working lens in diopter. So if you are doing the retinoscopy at 66 centimeters, the working distance calculation or the working lens will come to about 1 by 66 in meters. So this will be about 1.5 diopters. So whatever gross retinoscopic values you get, you have to subtract your working lens calculation, that is 1.5 diopters, and you will get the net retinoscopy values. Similarly, if the patient is sitting at 50 centimeters, then what will be your working lens calculation? It will be about 2 diopters. Okay. Similarly, if you're carrying it at 1 meter, then your working distance calculation will be 1 diopter, and you have to subtract this 1 diopter from the gross retinoscopic value. Now it is also called why it is called working lens. It is also called a working lens because some people, while doing retinoscopy, they will in the trial frame they are going to put the compensating lens before starting the retinoscopy, right? So if they are sitting at 66 centimeters, they are going to introduce 1.5 diopters before the procedure itself, and then carry out their retinoscopy on the pre-existing working lens. The problem with this method is that the reflex will actually become very distorted with so many lenses in place, and therefore it is avoided, and you can actually subtract this working lens later from your gross retinoscopic value after completing the retinoscopy without having any working lens in place. So that is the idea of the working distance and the working lens. Now let us try to do retinoscopy at 1 meter. Why have I taken this 1 meter is because this is already given in most of your textbooks, and it is very difficult to understand for most of the students. So now let us try to do it first in EMMETROPE. In EMMETROPE, we know that there is no refractive error and the rays of light are focused on the fovea, and the conjugate point or conjugate focus for the fovea is actually at infinity. Now we cannot actually sit at infinity for all the rays to converge at infinity. So we have a detector or a detective like this who is sitting at less than infinity. So what is he looking at? He's looking at rays which are not yet converged but will go and converge at the infinity. So for such a reflex, for such a nature of emerging rays which are not yet converged, what kind of reflex will you see? You will see a with movement reflex. That means if you move towards right, the reflex will move towards right. If you move towards left, the reflex will also move towards left side. And what do you do when you have with reflex? You will add the plus lenses. Okay, so in this case, say we put 1 diopter lens and we notice that the patient now is having a fully illuminated pupil. So what will be your gross retinoscopy value? Your gross retinoscopy value will come 1 diopter. And what was your working distance? The doctor is sitting at 1 meter. So what is the calculation? 1 by 1, it comes to about 1 diopter. So you have to subtract 1 diopter from your gross retinoscopy value, which was +1. So +1 minus 1 diopter will come to 0. So it indicates that the patient is actually an emmetropic patient. Now what about in a patient who is having, say, myopia of 1 diopter? Now if a patient has myopia of 1 diopter, what does it mean? It means that the rays of light are going to come to focus at a point which is 1 meter from the eye. Okay, like this. Okay, the focal point is also going to be 1 meter like this. Now, what did I tell you? The doctor itself is sitting, the doctor himself is sitting at a distance of 1 meter from the patient. Now, what is happening? All the rays are actually converging onto the doctor's pupil. So, what will happen? We will have a neutralization reflex already. So, neutralization reflex will be there without introducing any lens. So, the gross retinoscopic value will be about 0. Okay, and now if you subtract the working distance of 1 diopter, how much error you get? You get 1 diopter, and this is correlating with myopia of 1. Let us see in a patient who has myopia more than 1 diopter. So what does it mean? More than 1 diopter means, say the patient has myopia of about 1.5 diopters. So where will the image be formed now? The image or the rays will actually get converged at about 66 centimeter, which is very less than 1 meter, that is 100 centimeters. Okay, but where is the detective sitting? The detective is actually sitting at 1 meters, right? So what is he looking at? He's looking at the rays of light which have already converged at 66 centimeters. So when such a thing happens, I already told you that you will get against the movement, or you get against motion. That means if you move the retinoscope towards right, the image will move towards the left side, and if you move the streak of light towards the left, the image will move towards the right side. And whenever you have against the motion, what is the mnemonic? The mnemonic is add minus lenses. So you start introducing the lenses, you will use minus 2.5, and then increase it in steps of about in steps of 2.5. So you will be introducing minus 0.50, minus 0.75, so on and so forth, till you get the neutralization point. Okay. Now, say suppose in this patient you get this neutralization point at a number at the lens of about minus 0.50 diopters. So from this, again you have to subtract the working distance, which is 1 diopter. So the net error that you get in the retinoscopy is 1.5 diopter. Right? So this is how you calculate retinoscopy in a patient, and this is the concept in a patient who has myopia more than 1 diopter and you're doing the retinoscopy at 1 meter. Now, what about a patient who has hypermetropia? In hypermetropia, the image is formed beyond retina and the far point is beyond infinity. That means the rays of light are never going to actually converge. If you make an examiner sit there in between the infinity and the eye, what will happen? You will get with motion, and then you have to add the plus lenses, and then you will get the neutralization point. So suppose you get the neutralization point at about plus 2 diopters. Again, you have to subtract the working distance of 1 diopter. So the net hypermetropic error that you get is 1 diopter. So what are the characteristics of neutralization point? So at a point of neutralization, when the pupil is totally filled up, the reflex will actually be the brightest, the widest, and the fastest. Okay, if it is moving, it will move really fast, and sometimes you might even not be able to detect that movement, and you will say there's no movement on the neutralization point. And the reflex will be really bright and it will be widest. That streak will become really wide. And as you move away from the neutralization point, the reflex will become slow, it will be dull, and it will be very narrow. Okay, on the either side of the spectrum, whether it is against or whether it is with motion. So this diagram also reminds you that when you're sitting somewhere till the crossing of the lines or to the crossing of the rays, you're going to get with motion. Okay, and when you are actually sitting beyond that neutralization point, you're going to get against motion. Okay, and then as you're away from neutralization, the reflex will be slow, it will be dull, it will be narrow, and as you reach the neutralization, it will be fast. That is the speed, the intensity, that is bright, and the shape and the shape of the band, which will be more wider. Okay, so that is important. For practical purposes, remember that with means you have hypermetropia and against means you have myopia. If you have against, you have to add the minus lenses, and if you get with motion, you have to add the plus lenses in order to reach the neutralization. Now that's all for this lecture, and if it was useful, kindly share the knowledge. Thank you and have a nice day.